Yes, it is.
Okay, good. Thank you.
Okay, good morning. We start a new chapter, so if you were sleeping during the past two lectures, it's a good moment to wake up. The topic today will be complementary to what we have been saying till now, namely these collisionless phenomena of transport or related to the acceleration and what else. So I will start talking about the collisional part of it, and you might wonder why is this important if we said till now that these are not essential for instance, for this shock physics. Well, Pasquale Blasi at least mentioned, I think in the first lecture, that these are important at least for a couple of reasons. One is that through collisional phenomena, we get a diagnostic tool. Okay, so you emit some particles, photons, neutrinos, etc., and through the detection of these particles, you can learn something of what's going on there. Okay, so it's like having somebody phoning you and telling you about the conditions that take place there. And the second reason is that over very, very long time scales, for cosmic rays, propagating through the galaxy, well, the time scales may be significant, maybe for example, tens of millions of years, or even 100 million years. And then over these time scales, even relatively subleading processes are important in shaping, for instance, the energy spectrum of these cosmic rays. So at least for these two reasons, we have to take care of collisional processes. Now, a couple of things, a couple of generalities on collisional processes in a relativistic concept. Probably you're familiar with them, but I will repeat them. If you have, for instance, a two-body collision ending up in two-body or even multiple particles, this is some A and this is some B for the incoming particles, you can define some relativistic invariants. Probably the most famous variable is the S, which is the square of the energy in the center of mass. And if PA and PB are the four momenta of the incoming particle, their square is clearly, this is a Lorentz invariant, okay? PA square plus PB square plus 2PA PB. Don't get confused. In four-vector notation, this is equivalent to, say, P mu, okay? This is equivalent to, say, PA mu, PB mu. I hope you have seen this before. So if you write this down more explicitly, that's going to be M square A plus M square B plus 2 times EA, EB, and then you have 1 minus beta A, beta B cosinus of the angle between the two. Why this quantity is very useful? Because if you impose the conservation of this quantity across your collision, maybe AB in CD or even multiple particles in final state, you can find a relation between the incoming particle energies and the outgoing final state that you want. And typically, this will be used repeatedly today and tomorrow to find out some threshold energies for these processes to happen. Okay, so one example I can mention, and leave you this as an exercise, but actually Pasquale Blasi already mentioned it, and also the solution to this exercise. So if you were listening, you know the answer. If I have a collision PP, and I want to know what's the minimum, what's the threshold for a production of an antiproton, you can use this relation to know in the lab system you have an energetic proton hitting a target of a proton at rest, and I want to know what's the minimum energy for a proton to produce an antiproton. You can just apply this equation. With the right-hand side, the minimum number of particles that are required for this reaction to take place, accounting for baryon number conservation and for charge conservation. And then kinematically, it's very easy because at threshold, you can ask that these particles are at rest. So only the masses are important. Okay? If you do this exercise, you will find that there is a threshold, of course, and this energy is also justifying why, if you read some papers on antiproton production in cosmic rays, people tend to focus on relatively high energies. So far, so good. There is another thing that is peculiar of collisional processes in cosmic rays, and which is quite different from collisional processes in accelerators, like LHC. This is a topic of its own, okay, doing hadronic physics with cosmic rays. But I just want to compute another variable which will serve to illustrate the complementarity of these two channels. The other variable, which you probably also know, is another of the Mandelstam variables, if you know what I'm talking about. For instance, in a process where you have, again, the same thing, PA, PB, think, for example, of an electron scattering against a proton going into an electron prime of momentum PC, and the proton recoils with a momentum PD. I want to compute now not the central mass energy square, rather PA minus PC square, which is the square of the momentum exchanged in the process. Okay? That's what this variable represents. If I do this calculation, in this case, for example, specifically for the electron case, I would get what? Twice m the mass of the electron, because PA square is the mass of the electron, PC square is the mass of the electron, and then I will get minus twice the electron energy initial, electron energy after the scattering, and then I have 1 minus cosinus theta times beta E prime, the velocity of the electron before and after. In the relativistic limit, this is much larger than the mass. This velocity is basically 1, so I end up with basically minus 2 E prime, and then this is 1 minus cosinus theta. And this I can rewrite as minus 4 E prime sinus square theta alpha. Now, there are a few. A first comment is that this is negative. This quantity is negative, but I drew something that, for instance, is a photon exchange. So clearly, this is not an on-shell photon, because you know that if I write the momentum square of a photon, this is 0. Are you all familiar with this relativity notion? Here, I have an exchange. So the difference of PA minus PC is also the Q that is transferred. But this turns out to be negative. So clearly, this is an off-shell process. This is just a technical comment. It has nothing to do with what I wanted to say, but to keep in mind. The second thing is that probably you have seen in bachelor level or beginning master courses that in a very famous experiment, Rutherford discovering the nucleus, he got a cross-section for the scattering of alpha particles against a nuclear target, which was going as the charge of the alpha particles times the charge of the nucleus times alpha over energy square times sinus square theta over 2. There is maybe a factor 4 here, I don't remember. Okay, this is so-called Rutherford scattering formula, if you have seen it. If you don't, this is just describing the probability that a particle is recoiling by electromagnetic interaction when shot against a target. And you find, sorry, there is a fourth power here, sorry. This is exactly describing, again, the diffusion of these particles, in his case against nuclei. and you get exactly the same factor squared in this formula. This is not such a surprising result, because from the quantum point of view, this is proportional to 1 over t squared. If you don't know what I'm talking about, don't worry too much. The only thing I wanted to say is that in this cross-section, there is this dependence on sinus fourth of the angle, which means that the cross-section is very large when the angle is small. Okay? What does it mean? That most of the events will be small angle scatterings. Okay? Which means, from this relation, that they correspond to a relatively small t. So most events are characterized by a small momentum transfer. If you want to find new particle at LHC, that's not at all what you are interested in, right? What you want is that the momentum transferred is sufficiently large to exceed some threshold for the new particle to be produced. If you do not release enough energy, the new particle cannot be produced on shell. And what it means is that typically in cosmic rays, this is just an example, but it's a characteristic of something which is frequent in cosmic rays, namely that the cross-section part you are mostly interested in is the cross-section that dominates the rate. The regime of the cross-section you are interested in is, in this case, the small angle scattering, because that's what dominates your rate of events. And this is very different from what happens in collider searches for new physics, where it's the rare events with a large momentum exchange which are relevant. Okay? So even if you might wonder, I don't know, Pierre Roget Observatory is actually looking at events where the center of mass energy is very, very large. Okay? We are talking about showers induced by cosmic ray having energies of 10 to 19 electron volt, 10 to 20 electron volt. And by the way, I invite you to compute what is the equivalent center of mass energy of these events. And you will discover this is way above what the LHC, for instance, is probing. Despite this fact, the observables we are mostly sensitive to in cosmic ray experiments are not probing the same regime of the cross-sections as the LHC is probing, are probing a small momentum exchange regime. Okay? So this is another comment which probably won't be useful for you till next week, when you will see something about ultra-energy cosmic rays and showers and all that, but keep it in mind. One application of the formula I just wrote about the center of mass energy concerns a process that has been mentioned by Kota yesterday, namely the pair production. Photons of very high energy propagating in the interstellar space, or more often in the intergalactic space, hitting some background photon and producing a pair. Okay? Now we can apply this formula to know what's the threshold for this process to take place. Okay? So in this case, it's easy. It's even easier because the mass of the two photons is vanishing. So we just impose that twice the energy of the high energy photon times the energy of the background photon times this angular factor, which is just 1 minus cosinus, must be larger than the threshold to produce this particle. And what is this threshold? Well, it's the value for which this thing here is minimized, okay? So you will have me squared plus me squared plus twice. This is basically me squared, because the lowest values for this case is when the energy is basically the mass and there is no momentum, okay? And here the maximum value will be 2. So at the end of the day, we get the condition that E of the high energy photon must be larger than me squared over epsilon for the threshold to take place. Unless I forgot some factor 2. I invite you to evaluate numerically this expression. And you will discover that for a background, say, of microwave energies, like the CMB, where this number is 10 to the minus 3 electron volt roughly, you get a typical energy which is of the order of a fraction of a PeV, hundreds of TeV or something like that. And if you have a typical energy which is optical or infrared or ultraviolet, let's say electron volt scale, you will get a typical TeV scale for the impinging photon. What does it mean? It means that if you have energetic photons which are, say, of TeV energy, then they will start reacting with optical light, with the starlight, with the extragalactic background light I was mentioning at the beginning. And if you have photons which are as energetic as PeV, they will feel the much more abundant microwave background photons. As a result, the sky will become opaque to gamma rays. Okay? So the extragalactic gamma ray astrophysics, these type of messengers, these photons, can only come to us from far away if their energy is below some values. Okay? In particular, for very, very far extragalactic objects, this must be well below the TeV scale. And actually, if you go to PeV, even our galaxy starts to become opaque to gamma rays. So at the end of the day, at PeV energies, you only see galactic objects, maybe nearby galactic objects. Okay? So this is a simple exercise that you can do to tell you that there is some limitation on how much you can push the ground-based gamma ray frontier. Okay? Situation evolves a little bit at very ultra high energy, but I won't cover this. There is an associated interesting process that I think Compton mentioned, but I'm not sure, but which is initiated by that. You may wonder what happens once this process takes place in the extragalactic sky. You have a source of gamma rays. These gamma rays are energetic enough that they create a pair. What happens to this pair? Actually, this pair is still an energetic object, okay? These electron or positron are still very energetic. What happens is that they propagate in the extragalactic sky, and they will induce some of the processes I'm going to talk about. In particular, they can induce some inverse Compton scattering, namely E plus the background photons, not necessarily the same background photon, but some background photon in the sky, scattering into an E prime plus gamma prime. Or maybe in magnetic field, the electron can radiate. This is the synchrotron process I'm going to talk about right now. So this transfers some energy from the electron or positrons through the background to the background photons, which are upscattered. So what happens is that one step later, your electron will accelerate, if you wish, a background photon. This background photon may or may not be above the threshold for this to happen again. So if this happens, what you experience is a cascade. It's a multiplicative phenomenon, a little bit like what happens in the atmosphere for the showers of cosmic rays producing secondary particles in the atmosphere, but evolving over very large extragalactic distances. And there is plenty of physics associated to that. For example, based on this, we can infer some information on extragalactic magnetic fields and things like that. I won't talk about it, but be aware that what I'm talking about today gives you some tools to study this type of phenomena as well. Okay, and one thing that I didn't mention, but I can sketch, I don't know where, let's say here, just to describe what's the shape of the cross-section for this process and why I'm sort of using the threshold for a proxy of its efficiency. If you look at the cross-section as a function of the energy, basically the cross-section for this pair production cross-section behaves like that. And this peak, whose value is roughly 1/4 of sigma Thomson or so, happens at twice the threshold, roughly. So basically, as soon as this is allowed, the cross-section is quite efficient. So you can almost use the threshold for a proxy for the value of the energy at which this happens. That's just a comment I wanted to make. If you don't know what the Thomson cross-section is, I'm going back to that in half an hour or so. Okay, so let's start considering some collisional processes. The first one I'm going to treat is this one. This is the synchrotron process. Today we will focus on leptonic processes, namely ones involving electron and positrons. In particular, leptonic processes onto radiation or fields, B fields, not matter. Okay, these are probably the two most important ones for the topics treated in this school. Tomorrow we will move to hadronic processes, production also of pions, and the processes that Pasquale mentioned about Bethe-Heitler, pion production for GZK cutoff, and all this stuff. Okay. What are the key information I want to talk about for these two processes? Well, first of all, what did I tell you? What are these processes useful for? One, because they alter the spectra of the cosmic rays, in this case the electrons and positrons, through energy losses. So we want to know how efficient the energy loss is through these processes. The second thing is these processes are useful for diagnostics. So I want to know what's the typical frequency or energy of the photons emitted in these processes. So these are the two key quantities we want to master. Okay? Concerning the first thing, namely the energy loss through these processes, there is one formula from basic electromagnetic theory which I know, I need, and I assume you know. If not, in the notes I provide a 2-3 lines justification for this formula. And this is the Larmor formula. So the power radiated by a particle which accelerates or decelerates is 2/3 q square a square, where a is the acceleration. Okay. If you are not familiar with it, I can try to justify heuristically why this makes sense. Okay. First of all, well, the q square should appear there and at some point, because by definition a radiative process in terms of Feynman diagrams, for instance, is associated to a vertex of this type. Each vertex of this type has to do with a coupling, which is the charge. This is the amplitude. The cross-section must be the square of this, so there must be a q square appearing. No doubt about this. If you don't know what I'm talking about, just forget and accept that this is there. In any case, it's dimensionless in my natural system of units. Okay? The acceleration. Why it should depend on upon the acceleration? Well, electromagnetism is strictly linked to relativity, right? This is something quite objective, so to speak. The presence of an additional particle, a photon in a final state. So it cannot depend on the velocity. Because I could just go to a different frame, and then in that frame the particle has a zero velocity, and then this should not be there. Clear? So it must depend on the velocity. Why? On the acceleration. That's the first kind of kinematical quantity it can depend upon. Why acceleration square? This makes sense from a dimensional point of view. This is the power radiated. So dimensionally, this is an energy emitted per unit time. But in natural units, you see why it's so powerful then. In natural units, inverse time is energy. So this is dimensionally, this is equivalent to 1 over time square, time square, or if you wish, energy square. What is acceleration? Acceleration is velocity over time dimensionally. Velocity is without dimension. So dimensionally, this guy is 1 over time, or if you wish, energy. So the only power this can depend upon is the square. Okay, because I want this to be dimensionally equal to that. Okay. This is not a way to derive it, but at least makes sense. Now, you know that there is an acceleration associated to a motion in a magnetic field. So there should be some power radiated. This is, by the way, the origin of this gyro frequency I was mentioning in I think the first lecture or so. This has to do with the typical frequency of emission of this system. We are interested, however, into a relativistic case. In the relativistic case, the Larmor formula is still valid. The only difference is that this acceleration has to be replaced by the 4 acceleration. So the acceleration has to be replaced by the 4 acceleration. But apart from that, which means that a square has to be intended as mu, a mu. What is the acceleration? Is a force over mass. What's the force experienced by a particle which is moving with a gamma factor gamma with respect to a magnetic field? Well, we go back to this induced electric field. So it's just in a relativistic context. So this is the same equation written by Pasquale a few minutes ago. So you have some minus gamma v cross b. The acceleration is going to be the force over mass. The force is QE over mass here. And so the acceleration square is going to be Q square E square, which is actually gamma square V square B square sinus square of theta over mass square. You multiply times 2/3 Q square, and you get the power. So the power emitted by synchrotron radiation, which is the process, not this one, sorry. Yeah, this one, the second one. This is nothing but 2/3 Q to the 4th power, gamma square over m square, v square, b square, sinus square of theta. And of course, v is basically c. So it's basically 1 in this formula. So the dependence for a relativistic particle. So the 2 ingredients that you should pay attention to is this dependence upon b square and this dependence upon gamma square, which for a relativistic electron will go as the energy of the electron over the mass of the electron square. Okay? So this is the amount of radiation emitted by a relativistic electron. In principle, also protons, of course, experience this process. But since there is this mass at the denominator, you see immediately that synchrotron radiation by protons is way less efficient than synchrotron radiation by electrons. Of course, muons, in principle, also experience that, all charged particles. And these will, keep in mind these 2 informations, okay? Gamma square and b square. Because this is till here, it's a purely classical electromagnetic type of derivation, but this admits a particle interpretation. I will come back later on. How is this radiation emitted? From the geometrical point of view. So you have a particle which is accelerated or decelerated. This is associated to some radiation. How do we see this radiation? For instance, imagine that there is a process which emits some radiation isotropically in the frame of the emitter, say gamma ray burst or whatever. Would we see it isotropically if there is a relative boost between us and the frame? How do you see it? It was mentioned and showed actually in picture by Kota. This will be a very beamed emission. How beamed? Well, it depends on the Lorentz factor of your system. Okay? So a simple way to understand this concept is to remember or to rederive, if you have never done, the aberration formula for relativity. So how do velocity transform under a Lorentz boost? So remember just the time and space transformation law under a boost. You have that T prime gamma T minus beta x, and you have that x prime is equal to gamma x minus beta t. From this, you can derive the link between the velocity components in the primed and unprimed frame. Okay, what I'm talking about the ux prime, uy prime versus ux and uy. Let me write briefly this. Probably, how many of you are completely familiar with what I'm saying, and so this is very, very boring? None. Wow. How many of you are listening to what I'm saying? None. Okay. Which is a special Indian bread, right? So if you just compute ux and uy, which is nothing but dx over dt, this is the definition of ux. This should be rather trivial. Have you ever seen this aberration formula before? Let me get to it. I think you should have. For 1 plus beta ux prime. And then you do the same thing, uy dy over dt. Of course, here there is no transformation because I'm assuming that the boost is along the x direction. So this is just dy prime, but there is a dt prime, so there is a gamma dt prime plus beta dx prime, and this writes uy prime divided gamma plus 1 plus beta ux prime. And so if you have some emission which is isotropic in the primed frame, what does it mean? The angle of a photon emitted in this is given by uy prime versus over ux prime. This defines basically the tangent of the angle of emission in the prime field. Well, the tangent of the angle of emission theta in the unprimed frame, uy over ux, this is going to be, well, from that it's u1 prime over gamma ux prime plus beta, and this is u prime sinus theta prime over gamma beta plus u prime cosinus theta prime. Are you sure you have never seen how velocities transform in relativity? Yeah. That's what it's useful for. Huh? So you imagine that now a photon is emitted at an angle theta prime equals 0. Theta prime equals 0 in, let's do a little sketch. Imagine that there is this observer here, and let's call this theta 0. So a photon emitted at theta prime equals 0 will be seen at a theta, which is again 0, okay? Fine. What happens to a photon which is emitted orthogonal to that, okay? So that this is pi half. Nothing. Huh? So in fact, you can work out this shape, and it turns out that in the frame of your boost observer, the emission would look more like that. Huh? With a typical angle, I'm really bad at drawing, but the typical angle of this thing, this angle will be 1 over gamma, which you derive from here. This is this 1 over gamma that appears here. In general, for an arbitrary shape, you can use this formula to draw this sort of drop type of deformation. So why do I need this for going on with the physics of the synchrotron radiation? Because if you are in a non-relativistic limit, this effect is not there, so you have a charge that is moving around your magnetic field. What's the frequency of this motion? We already computed it, okay? The frequency of this motion is the gyro frequency, okay? So what is the only time scale of the problem is this orbital time scale. Oh, this I would need later on. Let me just erase this, okay? So the spectrum of the emitted emission in the non-relativistic case is very trivial. It's just monochromatic. Huh? It's just monochromatic and peaking at this frequency, okay? The gyro frequency. Here, however, there are some complications. The first one is that you don't see a continuous emission, in principle, from your object, okay? Why? Because of this beaming effect. So there is only one small angle of the order of 1 over gamma through which, in the orbit of your particle, let's say that we are here, there will be only an angle of semi-aperture 1 over gamma through which you will see the signal because of this beaming, okay? What's the typical duration of this signal? Why do I need the duration of the signal? To do the calculation properly, in order to compute the spectrum of emission, what is the spectrum of emission? It's basically the Fourier transform of the time dependence of my emission, okay? Now, I don't want to do the Fourier transform. This shocked some of you, so instead of doing the Fourier transform, I just do the poor man Fourier transform. If I have a process of a time scale delta t, the typical frequency will be 1 over delta t associated with that, okay? So I need to know how long my system is emitting from my point of view as an observer, okay? So you have a particle which is rotating in the magnetic field, but I only see it for a duration delta t, which is going, let's call this A, this B. This duration delta B is nothing but going to be, the length of this is going to be AB over V. Makes quite sense, okay? What is AB? Well, AB is going to be the radius, which is my relativistic Larmor radius in this case. The argument can be repeated for any other radiation associated to a circular motion, actually. The AB is going to be RL times the arc length, which is twice 1 over gamma. So this is 2RL over gamma, okay? Now, when I am an observer here, there is another effect I should take into account, is that the signal traveling from B has to travel less time than the signal traveling from A. So in fact, the duration of the signal seen from the observer point of view delta T observer is going to be what? Is going to be the time of emission B plus the delta time B propagation from B minus time A plus delta time A propagation. And what is the propagation speed? That's the speed of light. If I do that, TB minus TA is delta T. Delta TB minus delta TA is just AB over the speed of light. So this gives me AB 1 over V minus 1 over C. Okay? Which I rewrite as AB over V 1 minus beta. And this result I can also rewrite in a burst of creativity as AB over V 1 minus beta square over 1 plus beta. This can be rewritten as AB over V 1 over 2 gamma, basically squared. This is the denominator of the gamma. And this, since I'm relativistic, is basically 2. Okay? So this is 1 over 2 gamma squared. And then I use that formula to make explicit AB. So this turns out to be RL over gamma cube. So we have basically learned another fact. Where should I draw it? Maybe here. I don't need this anymore. The other fact of the synchrotron radiation is that there is a typical time scale for the observer point of view, which is what I wrote. Twice the relativistic Larmor radius over gamma cube. Okay? So what is the typical frequency of the synchrotron? This is going to be 1 of delta T observer. This is my poor man Fourier transform. And if I remember the fact that RL was gamma times the non-relativistic, the non-relativistic results over gamma, what enters here is gamma cube over RL, which from lecture 1, I think, is nothing but gamma square omega over 2 pi, or if you wish, gamma square, this I was calling gyro, gamma square nu, the gyro frequency. Okay, so compare with the non-relativistic calculation, which would give us a monochromatic spectrum at the frequency at which your particle is rotating. In the relativistic case, you get a gamma square enhancement. Okay, that's the result. Actually, that's really a poor man approximation. The true result actually leads to a spectrum which is not monochromatic anymore. It has a shape which is nu to the power 1/3 e to the minus nu over critical energy. A critical frequency, sorry, but this critical frequency, which, if you wish, looks not at all. Something like that. It's not a delta, but roughly this critical frequency is this, where the peak is the frequency of synchrotron which I have computed, give or take a factor of order unity. Okay, so we know roughly at which energy the photons associated to this loss of energy in a magnetic field is falling. So now that you have your whatever radio telescope or X-ray detector or what else, you can look for synchrotron radiation at this frequency. Okay. Final information on that is the link between the spectrum in synchrotron and the spectrum of the electrons that are emitting it. Okay? As you have seen many, many times, typically people assume, because it comes out, for instance, of acceleration theory, that the electrons have some energy spectrum proportional to it's a power law, okay? E to some power alpha. What's the power law of the synchrotron emission associated to that, if it's a power law, by the way? What's the spectrum of synchrotron radiation associated with that? Intuitively, each electron will be emitting a frequency given by that, so you should compute the convolution of the two. Huh? So you have an electron of a given energy, and this gives you a certain frequency. An electron of another energy gives another frequency. Given the link between the frequency of synchrotron and the electron energy, you can compute this link. Okay? Let's do a simple estimate of that. So the key relation is nu s is given by the gyro frequency times gamma square, which is E over the mass of the electron square. From this, we get the differential d E is d nu times m over twice the square root of nu times nu g, which means that the emissivity and thus the spectrum of your synchrotron radiation will be given by what? Will be given basically by, it's proportional to the power, the synchrotron power, times the spectrum of the electron, NE dE. But the spectrum of the power, we know how it goes. This goes as E square times B square, the power in synchrotron. And E goes as E to the minus alpha. And then we use this relation to rewrite the dE in terms of d nu. And this is proportional to nu to the power 1 minus alpha over 2. B 1 plus alpha over 2 d nu. So it's not the same, but if you measure the radio or whatever spectrum, you can infer the spectrum of the electrons that have produced it. Okay? This is exactly fulfilling what I was telling you. You can use these objects as diagnostics for the accelerated particle at the source. Okay? Because you cannot go to the supernova remnant or elsewhere and measure the electrons directly. You can measure the photons. Okay? The photons come from this loss. Okay. So far, so good. Let's move to the other important process that I mentioned today, which is the inverse Compton. The inverse Compton is this upscattering of background photons by high energy electrons. Okay? We will repeat more or less the same story. We want to know what? We want to know the power lost. Yes, there is a question.
When you do your burst of creativity.
This one?
No, on the right hand side.
This one?
Yeah. Where did the V go?
Here.
No, up there.
Here? Ah, no, sure. It's C. Already here, I'm doing the approximation. Yeah, I should have been explicit. Of course, if there is a difference, 1 minus V, it's important. But if I have something like 1 plus beta, this is 2 for me. It's not exact. Anyway, this is not exact. But, the correction to that is going to be very, very small. Okay, inverse Compton. Inverse Compton, I think this I can erase. Anyway, all this is in the notes. Just try to be attentive enough to catch the argument, and please look at the notes here, because if you open the textbooks, this is done in a much more complicated way. Once you have understood the notes, then you go to textbooks and learn how to do Fourier transforms. Okay, inverse Compton is this other process. Electron upscattering a background photon, gamma prime plus A prime. We want to know the power that goes in this process, this loss process. Of course, this is a loss process if your electron has an energy which is much larger than the photon background into which it propagates, otherwise not. Again, what is the key formula we have to use for the power? Larmor formula, 2/3 q square acceleration square. And I will do this calculation classically first, and then interpret it in a quantum sense. So classically, you can perform a calculation for this process, but what is a photon classically? This is an electromagnetic wave. So I'm going to ask myself, what's if you have an electromagnetic wave hitting an electron, this will start oscillating according to the electric field it feels. So since it starts oscillating, there is an acceleration, so there is a power which is impinging over the electron from the electron point of view, and there is a power radiated by the electron because it's accelerating. Okay? What's the acceleration in presence of an electromagnetic wave? Let's put first the case of a low velocity electron. Well, the Lorentz field, the Lorentz force is nothing but QE plus V cross B. But since V in the non-relativistic case is small, we basically can forget about this and just compute the acceleration associated to electric field. This is exactly the same calculation as before. For being concrete, let's say that the electric field of my wave is E0 times some sinus. This is a plane wave, the simplest case I can conceive. So the acceleration is going to be the force over the mass. And in particular, the average acceleration, because that's what I'm caring about, is going to be Q E0 over the mass times, well, no, sorry. This is not a quantity of interest. What is a quantity of interest is A square, okay? Because this is what enters in the average power radiated. 2/3 q square average acceleration square, okay? So the acceleration square is what? Is q square. What is the average of the square of this? It's 1/2 E0 squared, okay? E0 squared over 2 m squared, and this is the acceleration square. You plug into this expression, and you get the power. So the power okay, will be 1/3 q to the 4th E0 squared over m squared. So far, so good. Now, if I want the classical definition of the cross-section associated to this process is the ratio of the radiated, so the outgoing wave with respect to the impinging flux. So the definition, the classical definition of cross-section would be the average power over the Poynting flux. If you don't know these, just ignore what I'm saying because you just accept the result of the cross-section that I am computing. If you know some classical electromagnetism, that's the definition of the cross-section in this context. What is the Poynting flux? The Poynting flux is E cross B over 4 pi. I compute its modulus. The modulus of S is E0 square over 8 pi because of this factor. So it's basically the product of these two. This is giving me the same normalization, apart from the fact that there is a factor 2 coming from the averaging. Again, this is something averaged. Okay, once I compute this, I will end up with this result, 8 pi over 3 q to the 4th over m squared. And if I plug in the charge and the mass of the electron, this is nothing but the Thomson cross-section. Okay? This is just to show you that the Thomson cross-section can arise purely classically. I didn't talk about collision of an electron with a photon, etc. This is the movement of an electron in a plane wave and the associated radiated power. But even from the classical point of view, I can rewrite the result for the radiated power in a different form. Okay? Let me erase here. What is this different form? What's the energy density in the electromagnetic field? How does it scale with the fields, the field strength? Huh? Yes. So the energy density in the electromagnetic field, the average one, is square over 8 pi each plus b square over 8 pi. In general, this is going to be, for our case of the plane wave, this is going to be E0 squared over 8 pi. So I can rewrite these or these. The average power through inverse Compton, writing it this way, sigma t times u, where u is the energy density of my electromagnetic field. And this is now a much more interesting expression to probe and to interpret. Why? This is the energy density in the field, which is, in terms of a quantum interpretation, the product of a number density times the average energy of my quanta. So you can interpret this inverse Compton power as the result of a collision of my electron with some target times the typical energy of these objects. And if you were to do a quantum calculation of that process, by the way, for those of you who know, it amounts to compute the amplitude. Well, no, that's the amplitude of these two, diagrams. You square and you do the standard QED calculation, you would get the same result in the classical limit, which I will go to define soon. And by the way, there is also an analogy with what we found before, because I kept this. There is again you see here there is some b square. And b square is again the density of energy in the magnetic field. So these two processes are actually much, much closer than it looks like. Till now, I consider an electron which is moving at relatively low velocity. How does this generalize to an electron which is moving with a large velocity? I use a trick here. Let's erase this one. The trick I'm using is that I'm computing a radiated power. Okay? So this is, I told you, the energy emitted per unit time. And if you remember some relativity, you know that the energy and the time transform the same way under a Lorentz transformation. So this is not a proof, but trust me, this is basically a Lorentz invariant. So I know that in any other frame, this is still writing like sigma t times u tilde. The only trick is to write this in the frame of interest. Okay? So I need to know how to transform the energy density properly. Now, how does an energy density transforms? An energy density, I told you that dimensionally is an energy times a number density. The energy, we know how it transforms. How does a number density transforms? Well, a number density is such that n times d cube x is a number of particles. A number of particles is a Lorentz invariant. Okay? So if I have a boost, it means that these will transform. This one is n dx, dy, dz. Two of these do not are trivially transformed. So n will transform like the inverse of x. And then another way to understand how it transforms is that dt d cube x, this is the 4 volume, which is also a Lorentz invariant. So you see that n must transform like this, like a time. A time transforms like energy, so basically this transforms like an energy square. So I'm just writing u tilde as u gamma square times an angular factor that I'm not going to bother right now, but in the notes you will find all the derivation. We have to do the average over these angles. And then in order to compute the energy loss of interest, so the minus dE over dt, remember what I'm doing is, instead of computing the inverse Compton energy loss directly in the frame where the electron is moving relativistically, I use the result I know for the case of non-relativistic case, and I'm transforming in the relativistic case. Okay? So basically, this will be given by what? By the scattered power minus the impinging power. So you have to do some angular averages minus the impinging power of your wave, and as a result of this, I'm not doing all this calculation, but trust me on that, you get 4/3 gamma square u sigma t. I just wanted to convince you that this u gamma square comes from this argument. That's the only thing I care about here. Okay? So again, we found that the power lost through inverse Compton for a relativistic electron goes as what? As the energy density of your background photon field times some gamma square times a number that comes from this algebraic manipulation. This is exactly the same dependence that we found here. Gamma square times field square times a density in the field. In fact, from a fundamental point of view, these two processes are basically the same thing. The only difference is that in this case, you are upscattering a real photon. In the other case, from a fundamental point of view, what you have is an electron in an external magnetic field. This is the typical QFT notation, which is radiating. So if you wish, this is a virtual photon, synchrotron. This is a real photon. That's it. So it cannot be very different. Of course, practically speaking, the energies are quite different for typical backgrounds of, say, optical or ultraviolet photons with respect to a B field which is associated to, for typical astrophysical objects, to photons of much lower energies. But apart from that, they are fundamentally the same process. Okay? Of course, there is a more proper way to do a general calculation, which is this one. You do the quantum calculation, you compute these two amplitudes, you sum them, you square, you get the amplitude square, and that's the cross-section. If you do this more advanced calculation, you get to the so-called Klein-Nishina result. That's the cross-section computed in 1929, I think. Few years later, just after the QED, the quantum electrodynamics, had been basically formulated, which reduces to the Thomson cross-section in the limit where the energy of your photon is much smaller than the mass of the electron. This is the classical limit of your theory, so to speak. Okay? So if the energy of your photon, well, what you have to make sure of is that the upscattered. Okay, one way to check this result, to assess the domain of validity of this result, is that the upscattered photon energy should not carry a much larger fraction of the electron energy than it can. Okay, so you see immediately from here. Let me answer operationally to your question. Okay. This, if it's interpreted the way I was mentioning, this is 4/3 gamma square energy of your background. Well, I have to introduce another notion. I didn't want to answer to your question right now, but basically, the energy of the photon upscattered will be given, the average one, will be given by this 4/3 gamma square background photon. Okay? So clearly, this formula is valid in the Thomson limit. This cannot be larger than E by conservation of energy. So the condition that this is smaller than 1, the incoming energy there is equivalent to say that this one incoming in the frame of the electron. Epsilon E is the incoming photon energy in the frame where the electron is at rest. Okay? This one, in the laboratory system, is equivalent to require that the upscattered energy of your photon is well below the initial energy of the electron, which makes sense. Okay? You pushed me to anticipate a little bit one thing, but it's fine. It's perfectly fine. So instead of doing this calculation, which requires QED and probably 2 hours, how much time do I have left? 5 minutes. Okay, 5 minutes. I just want to derive these results that I mentioned to you without proof kinematically. Okay? What does it mean to do the Klein-Nishina type of calculation? It means assuming that you have a collision between an electron and a photon. You see from that diagram, by the way. So it means that I can write down some kinematical constraints in this process, like the conservation of energy and momentum. And this will give me some link between the initial energy of the photon and the final energy of the photon with respect to the angle, for example, of the scattering. Again, I guess that you have seen some of these in basics of quantum theory or something like that. But if I call my, okay, these I call Pi, these I call Ki, these I call Pf, these I call Kf, I have that Ki mu plus Pi mu equal Kf mu plus Pf mu. Okay, that's just energy momentum conservation. Also, I know that these are on shell, so Pi square equal Pf square equal Me square, and I know that Ki square equal K final square equals 0, again on shell photons. Shell means light-like. So I know this relation Me square equal Pi plus Ki minus Kf mu Pi plus Ki minus Kf mu. I impose these things, and I get that Me square is equal to 2 Pi Ki minus Pi Kf minus Ki Kf, 4 vectors contracted. Then in the frame where the electron is at rest, Pi I write Me0, 0, 0. Then I choose the x-axis as the direction of the incoming photon. And then the outgoing photon will be in a different direction. And I will call the direction generated by the two the xy plane. So in this case, I can write the Ki as simply epsilon I 1, 1, 0, 0. And the Kf as epsilon f 1 cosinus theta sinus theta. So theta describes the angle between the incoming direction and the outgoing direction of your photon. And rewriting this, I get this relation. So I have no time to do all the steps, but it's algebra you can do as an exercise. Epsilon I 1 plus epsilon I. Remember, epsilon I is the energy of the photon in the frame where the electron is at rest. Me 1 minus cosinus theta. This is the link between the outgoing photon energy and the incoming photon energy in the frame where the electron is at rest. Depends, of course, on the angle of emission. What happens in the frame where the electron is moving? Not surprisingly, there is a boost. So what will happen is that there is an epsilon E prime, which is nothing but some epsilon E gamma 1 minus cosinus alpha times the beta of the electron. I don't care about this because it will, I mean, one can perform some angular average at the end, and so what matters are these gamma factors, okay? So if we want to rewrite this relation in the frame where the electron now is moving, we want really a relation between the epsilon final prime and the epsilon initial prime. The epsilon initial prime is just given by a boost with respect to the initial epsilon. And not surprisingly, if you want to express now, so I can rewrite this in terms of epsilon prime. Okay? Then this gives me the final energy in the frame where the electron is at rest in terms of the energy of the incoming photon in the frame where the electron is moving. I want now the final energy in the frame where the electron is moving. So I have to take this epsilon f expressed as a function of epsilon y prime and boost it again. I will get what? Not surprisingly, I will get a factor gamma square that comes in. One gamma from this boost, and the other gamma from replacing this in terms of the epsilon prime. Okay, that's the only trick, and there are some angular averages that more or less I try to describe in the notes. But basically, the final result that you will get is that in the frame of the lab, the photon energy upscattered, now forget about all these primes, etc., is going to be gamma square the energy of the incoming photon. This is the final result, okay? I don't want to use prime for the final results. This is valid in the Thomson limit, which means analytically, when in this game, I'm neglecting this piece here. I'm saying that this is small. If you wish, let's keep it for the sake to avoid confusion right now. So if I neglect this, that's what I get, which is exactly the same type of argument I was writing here before. There is this numerical factor that comes from these averages, and I didn't want to make. If it's not, what happens? If it's not, I will just tell you in words. If it's not, you can compute anyway the amount of energy even in that case. If it does not happen, if it's not in the Thomson regime, two things happen. First of all, the cross-section that you can look on the notes or in books, in the Klein-Nishina limit, drops. So it's more difficult for the electron-photon interaction to take place. On the other hand, the energy that is transferred in the upscattering of the photon is much larger. Okay? So the electron interacts more rarely, but when it does, it loses a lot of energy. Okay? That's what happens. So in that case, you will get a large photon energy outgoing. So it's like a one strike of billiard balls or so. It's not a little diffusive loss of energy of the electron. That's, in words, what happens. If you repeat the same argument that I did before concerning the link between the energy loss spectrum and the electron spectrum, you will find exactly the same result. So again, in principle, if you measure the inverse Compton spectrum, you can infer the parent electron spectrum. Okay, exactly the same result, because this is the same formula after all. Final word is that this is extremely important in astrophysical objects, both processes, because a lot of objects in nature present either synchrotron emission or inverse Compton emission, or even both. The most famous example where you see clearly these both emissions are active galactic nuclei, for instance. I'm pretty sure if you do astrophysics, you have seen spectra rescaled by some energy power of these objects which look like double bumps. An emission which looks like that, or this, depending on the cases. There are blazars and whatnot which have this type of features. And the typical interpretation of that is that this is coming from synchrotron, and this is coming from inverse Compton. But it's not limited to these extragalactic objects. Even in the Crab Nebula, for instance, you have this type of emission. There is an exercise that I propose that is linked to this with some empirical data. There are even objects where we believe that the second bump is actually coming from inverse Compton of the photons that are emitted through synchrotron in this first bump. So your electron in magnetic field will emit some photons of synchrotron nature. The same population of electrons hits back on this and will upscatter to very high energy inverse Compton bump. Okay? This is called synchrotron self-Compton. Of course, not surprisingly, these kind of systems are sort of paradigmatic. Why? Because now you are assuming that the same population does both jobs, which means that many unknowns cancel. And so you can infer quite a lot on the properties of these objects if you are reasonably confident that this is what makes the spectrum. Okay, I will stop here and postpone to tomorrow the discussion of leptonic interaction with matter, okay?
You get a bonus. We downsize the minimum to 2 questions because we are in a hurry. So.
Sorry, but. Even 1. Now you have to ask a question.
No. Is Mari?
No.
So, hi, I was wondering, does this beaming effect of synchrotron radiation has the same nature that the beaming of Cherenkov radiation, or completely different effects?
No, Cherenkov radiation has to do with the fact, for the audience, that a particle moves in a medium with a velocity which is larger than the velocity of light in this medium, okay? There, I don't know if you call it beaming usually. There is just an opening angle of your cone, which depends basically on the refractive index of your medium, but it's not a Lorentz boost. At least for me, I would never hear of such a thing. And by the way, it's not specific of synchrotron radiation. Any relativistic emission, for instance, inverse Compton, would be subject to the same type of beaming if you have a very high boost with respect to the observer. So this has to do with the relativistic transformation. I derived basically the aberration formula, not with the process. It's true that from the nomenclature point of view, synchrotron radiation is by definition associated to a relativistic limit. Otherwise, you have cyclotron, or I don't think anybody talks of non-relativistic synchrotron emission because it's exactly it's cyclotron. Yes, you won't call it synchrotron. By definition, it's a relativistic phenomenon.
Thank you.
But we had some questions before. Huh?
There?
No, about the conditions of Klein-Nishina validity.
46 minutes for lunch. You have to ask a question. Unless we have time for lunch, the time is finished.
Ask something. Please stop him.
I'd like to wait 30 more seconds because we always ask questions, which is good. But I would like to give voice to someone that doesn't speak normally.
Now, maybe how is corrected that formula in the Klein-Nishina regime?
It's going to be linear in gamma, I think.
Okay.
Huh? Memory. It's right.
Okay, you get away with this just because we are in a hurry. Okay, we thank Pasquale again. Okay, so we have the colloquium from Professor Murase at 2 p.m. sharp, okay? That's here, so please really be here a couple of minutes before. I suggest you go for a sandwich at the canteen downstairs. You can do whatever you want. That's the fastest way. But please be here sharp because that's an instant thing. And there will be information related to the classes of the school, so it's not something else, okay? We talk about the presentations after the colloquium.